Hey, Chemisters, this is Mrs. Vandeloy bringing you another edition of Blank Wall Video. This is going to be chapter 3.1 through 3.4, and it should be very, very familiar with you from your first year chemistry class. All right, we're talking about molecules, compounds, and later on chemical equations. So if you think about chapter 2, what did we discuss in chapter 2? It's always been atoms. We talked about in section 2.9 the molar mass of atomic vanadium, the molar mass of atomic titanium. All right, what about everything else? Folks, there's only 118 elements out there, and really the last 20 of them we will never really see in our lifetime. So what about everything else? All right, how do we deal with everything that's a molecule or a compound? Well, that's what chapter 3 is going to be all about. So it says so far this year we've discussed only atoms and elements. That is only the tip of the iceberg, really it is, a drop in the bucket of what is out there. So let's check this out, section 3.1. And let's check this out here. We have a balloon. Right here is a balloon of some H2 and some O2. It says right here, if you can read that, this can have any ratio of hydrogen and oxygen. So they're gases, and you can put a little bit of oxygen gas and a lot of hydrogen gas in. That's what the Hindenburg was doing. Or you can make equal amounts or whatever you really want. Okay, so those are gases in this balloon. Notice their representation here. We have the red ones are the oxygen, the white ones are the hydrogens, and they are bonded atoms, aren't they? Okay, we'll talk about that a little bit later. So what about water? Here's a glass of water. It says water molecules have a fixed ratio of hydrogen atoms to oxygen atoms. All right, if you look at one of these pictures right through here, you'll see that there's one red sphere for every two white spheres. Okay, so let's kind of look down here. It says, what do you know about this? List what you know. Well, hydrogen's a gas, right? See those little zoomies going around, right? We talked about those earlier. It's a gas. So the red is a gas, the white is a gas. But what about this? Water is a liquid. Mrs. Vandeloy, water doesn't have to be a liquid. I know that, but we wouldn't call it water otherwise. We would call the solid form ice, and we'd call the gas form vapor. All right. So if I'm looking at that glass, it is liquid water. Well, what else do I know? I'm looking at some ratios here. Notice that the white one, all right, is hydrogen. All right. How do I know that? It's smaller than the red. Okay. And there are two atoms bonded together, so that's why it's H2. The red ones are bigger. They're your oxygens. And again, there's two oxygen atoms bonded together to make O2. And what about over here? Each water is made up of two whites and one red, H2O. All right, last but not least, I also wrote up that H2 is made up of the same element, so is O2. All right, so I'm going to like stick that over there in between. But what about H2O? Well, it's made up of different elements, and I'm guessing that's pretty obvious. All right, so which one of these, hydrogen, oxygen, or water, is not like the others? It's kind of like your Sesame Street song, right? One of these things is not like the others. One of these things doesn't really belong. I think you can finish that story. All right, so which one do you think is not like the others? All right, well, let's see here. If you said water is not like the hydrogen and the oxygen, well, they're made up of different elements, okay? What am I alluding to then? That we have a compound. A compound is when two or more elements combine, bond, if you want to put the word bond in there, to form a compound, an entirely new substance is formed, okay? Well, if you might remember from your first year chemistry class, all right, there's more than one type of chemical bond, all right? The first type is called covalent. Covalent is between nonmetals and nonmetals, okay? So what is the most common covalent molecule around? Well, if you said it was hydrogen, sorry, what am I saying? If you said water, you're right, okay? What's another very, very common covalent molecule, nonmetal? So everyone take a deep breath. All right, Now release it. What are you releasing, everyone? Carbon dioxide. And as you probably know, that has been in the news for a very long time as a greenhouse gas and how it can reduce the CO2 emissions. So you probably have heard of that. So carbon and oxygen are nonmetals. Well, I'm going to throw another one at you. All right, so how about C6H12O6? All right, that would be like fructose or glucose. They have the same formula, different structure though, isomers. Um, and those are all made up of nonmetals. Hey, what about table sugar? I could throw that one at. That's C12H22O11. All right, so they're all made up of nonmetals. Okay, you might want to add a few more to your own, but probably those are pretty common. All right, now it says draw a molecule of water. I think you've already seen that from the first section, haven't you? So do you recall I have one oxygen and two hydrogens? So that'd be my molecule. And what's so special about right in here I'm pointing to, okay? What's going on right there? I wrote, notice the hydrogens are attached to the oxygen. All right, there's a bond between the hydrogen and the oxygen. And what kind of bond is that involved? Sharing electrons. So you might be guessing that later on in this year, we'll probably be doing Lewis dot diagrams, and that's another what am I trying to say? It's another way to show sharing of electrons, all right? So let's go to the next page. Well, what's the other kind of a molecule, or in this case, a compound? So covalents are molecules, ionics are compounds, all right? So ionic is involved electron transfer from a metal to a nonmetal. So here's my sodium. Notice how it's arranged. Sodium is a metal, and it is the same atom in this very patterned like substance, all right? We do not talk about this in AP chemistry. A long time ago, we used to talk about how these metals are arranged. We could talk about body-centered and face-centered and things like that. That's out of the scope of AP, but that's an arrangement of all the sodium atoms put together in a metallic form. Okay, we will talk later about how the metallic is arranged, but just go with it for right now, okay? Over here is chlorine. That's my nonmetal. Notice it's a gas, all right? It's a diatomic. Remember that Hofbrinkel from beforehand? And so there it's Cl2s. And what's going to happen? All right, sodium loses an electron. Uh-oh, wait for it. Hey, sodium walks up to the bartender and says, help, help, I lost an electron. The bartender says, are you sure? And the sodium says, I'm positive. All right, so sodium is the metal. If you look at the correct table, it's on the left-hand side. It's a metal. It's going to lose one electron. We'll talk about why later. All right, and so my neutral sodium atom has 11 electrons. It loses one to have 10 electrons, so it makes the charge of Na+. Well, where does this electron go? Well, here's my neutral chlorine atom. It has 17 electrons. It's going to gain an electron, become negative. All right, so now we have the chloride ion. So look at this picture. So sodium atom gives its electron to the chlorine atom to make it a chloride or a sodium ion and a chloride ion. All right, so what now? We have the sodium ion here and this chloride ion there, and we're going to, oh, look at this, all right? Look at the visual here. So what's happened? The sodium, notice how it was all pretty like that, all arranged. Notice how the chlorine was a gas and it's only two at a time. Now it's arranged this way again, an ionic crystal. Okay, and that's what this down here is representing, the crystals, okay? And so what is the formula for salt? Well, you know what the formula is, NaCl. But Mrs. Vandewall, I don't see one sodium, one chlorine. I see lots and lots of sodiums and lots of chlorines. All right, so why is that? It's the ratio. You have one sodium that's purple to every one chlorine that's green, okay? So it's a 1-to-1 ratio. And we really don't call it let's say a formula. We call it more of a formula unit when you talk about ionic. There's not a huge distinction. Don't get all uptight about it. So, but an ionic compound is the ratio of the metals to the non-metals. So, picture this when you think of ionic compound, not one sodium with one chlorine, because this is what really is going to happen. All right, and so here's our sodium crystal, and there you go. So the question is, well, what are some other examples? Well, I came up with two of them. I have calcium chloride, and that's called rock salt. So come winter time, if there's a lot of snow and ice on your driveway, you may throw some salt on the driveway. It's not NaCl. Say it again, NaCl that you're throwing on the driveway. It's CaCl too. It's calcium chloride. Lithium fluoride's another one. Just a metal and non-metal put together. So again, think of this up here when you look up here. So this lithium fluoride would look just like the sodium chloride. You have one lithium for every one fluorine. But what would be different about the picture for calcium chloride? You would have one calcium, if that's the purple, and you have twice as many chlorines arranged here. So you couldn't fit it in this nice, cool looking pattern. It would have a very different pattern, all right? But that would still be an ionic crystal, okay? So moving right along, representing compounds, okay, we have chemical formulas and molecular models, okay? So we have different types of chemical formulas, and we have something called empirical formulas. Empirical is the relative number of atoms of each element of compound. So this is where you have your subscripts can no longer be reduced. So for example, these are all empirical formulas of certain compounds. So CH4 is actually methane, and it is already reduced. You can't reduce a 1 and a 4 any further. H2O, same thing. It's already reduced, a 2 to 1. NO, nitrogen monoxide, it's already a 1 to 1 ratio. CH2 truly doesn't exist. All right, it's an empirical formula, but there is no such compound, compound that has one carbon and two hydrogens. It can't work. All right, but that is an empirical formula. And then, as we said, NaCl, and that really goes to show here, if this is NaCl, I don't know how many sodiums are in this picture. I don't know how many chlorines are in this picture, but I do know this, it should be a 1 to 1 ratio. So that'd be the empirical formula. So when we talk about ionic formulas, it truly is the empirical formula of what's really going on. So what I'd like you to do now is write the empirical formula for each of the compounds represented by the molecular formulas. And we even have a case of an ionic formula in letter E. So what you need to do is look at the subscripts and reduce it to lowest term. So take a minute out, pause this, and come back when you're done. All right, how'd you do? Well, this is what I did. All right, so C4H8, I can reduce things by 4, so I got CH2. Carbon tetrachloride, you can't reduce any further. It's already a 1 to 4. C2H4O2 is a nice organic compound, and you can reduce it further to CH2O. B2H3, we can reduce to BH3. C5H12, that's actually called pentane, and you cannot reduce it. It is already in lowest terms. Now, this is a mercury Roman numeral 1 chloride, and this is an exception to the rule. That in this case, you don't reduce it because of the charges and how mercury 1 exists. Mercury with a Roman numeral 1 is only exist as a diatomic ion in that case, okay? So you don't reduce it. There's not many other exceptions, so it's just one you got to know. Does it come up in the AP? Hardly, okay? So let's go to the next page. And there are different representations of how to represent these molecules. Here's a molecular formula. Molecular formulas are very useful in many ways, but they really don't show me how it's structured. Hey, let me go to the page before this again. Like especially this compound right here. Do you know how it's put together? No, you really don't. You don't have a clue as to what's bonded to what when it's written as a molecular formula. All right, so it does have its uses, like if you want to find its molar mass or do something like that, it is very helpful. But if you really want to know what the structure is like, and structure will determine the function, the molecular formula doesn't help. All right, so let's go back to the other page. So the structure formula is a little more handy if you can see how things are arranged. The ball and stick is really a good three-dimensional model to see how the shape is affecting things. All right, so ball and stick may be preferable to the structural. If you want to see, is this tetrahedral? Is it, trigonal pyramidal, whatever. And then here's a space-filling molecule because folks, I hate to tell you this, if you have this conception that a bond is like a tinker toy here, like a stick, you're wrong. This kind of gives you more of an idea of how the electron clouds are overlapping, all right? So it has its benefits too, okay? So that's section 3.3, got one more to go. So it says an atomic level view of elements and compounds. And again, this is kind of an important idea because the AP really likes pictures that look like this. Okay, so this is a big deal to AP. So we really should talk about this. Okay, so we can talk about pure substances. And really, if you go back to your very beginning, if you find your notes to your first year chemistry class, you might recall what matter is. Matter is anything that takes up space and has volume. And then later on in chapter 1 of your first year chemistry class, we subdivided matter into two things. We can talk about pure substances or we can talk about mixtures. Well, we're just talking about the pure substances right now. And we can talk about pure substances, either pure elements or pure compounds, okay? So a pure element can be an atomic element, and that's most of them. So to be honest here, like basically 110 of them, of the elements, are going to be atomic, okay? You got to be careful with there are molecular elements. And I like to think of the diatomics in particular. There's more than that than just the diatomics, but that's the majority of the molecular atoms, or excuse me, molecular elements. Then over here, compounds. You remember how we defined a compound on the very front page of these notes? Two or more what? Different elements combined, okay? So we have molecular, which are your non-metal nonmetals, and we have your ionic, which is your metal nonmetal. So I just came up with some examples. So again, of course, I probably put vanadium first for a reason. We all know why. Carbon is monatomic. Magnesium is monatomic, all right? So then the molecular, in this case, I gave you two examples of diatomic molecules. Why would I give you the diatomic? Because that's what these pictures are. All right, two atoms. So we have hydrogen, we have oxygen, and there's a few more which I'm going to show you later, or just down below actually. Molecules, I think I've already referenced these: water, carbon dioxide, carbon tetrachloride, sugar. All right, are molecular non-metal nonmetals. If you're going to jot that down, and ionic, of course, are metals, nonmetals. Okay, so these are further defined down here. Oops, go away. All right, so atomic elements are single atoms as their basic units. Molecular elements exist as molecules, two or more bonded together. I call them Hoff wrinkles. There's 7 of those. So H2O2, F2, Br2, I2, N2, Cl2. Those are your 7 diatomic elements. They do not exist by themselves, okay? Typically. If they do, they're called free radicals, and we won't worry about that, okay? So for our purposes, those are your 7 diatomic molecules. Get to know those. You probably heard that before. And there's a few other cases of polyatomic molecules. Phosphorus exists as a P4, sulfur exists as S8, all right? So it brings us a total of 9 molecular elements, okay? Molecular compounds are, again, 2 or more differently covalent. What was covalent again? Non-metal, non-metal, bonded atoms, and that means they're sharing their electrons. An ionic, you have your cation ion, that's your positive ion, that's your metal ion, and your anion forming an ionic bond by transferring, like that picture on the other page of that, sodium giving its electron to the chlorine. It's referred as a formula unit as it isn't one cation bonded to one anion. Again, that's a really fine point there, but it is what it is. Now, many ionic compounds exist as polyatomic ions. Oh my goodness. Do you remember those 27 polyatomic ions we forced you to memorize in your first year chemistry class? Well, guess what? They're back. All right. So I just gave you, oops, a few of them. All right. So here's one of them is sodium bicarbonate. You might recognize that as baking soda. All right. Calcium carbonate is a different one. This is a polyatomic ion. It's limestone, all right? So, you know, your creek beds are made of calcium carbonate. And then here's another one. I just picked copper 2 sulfate because I use a transition metal. Notice I put a Roman numeral in there. Oh my goodness, is naming coming up? Well, yes, it is, okay? So again, these are ionic compounds. So again, you have a cation and an anion. Um, Every cation is going to be a metallic ion except for one, and you might remember that, and that was ammonium. So even though ammonium is NH4 plus, it's made up of nonmetals and nonmetals. Together, it acts like a cation. It acts like a metallic ion. All right, so that's why be really careful to define now an ionic compound. You have a cation and an anion. So it's all metallic ions plus ammonium. Okay, well, let's go to the next page. You're almost done. All right, so given two elements A and B, I made mine blue and red so they show up. If you want to make yours colored in and you know, without coloring it in, I don't care. Do whatever you want. If you have a highlighter, colored pencil, go for it. So how would you draw a picture of a molecular compound with the molecular formula of A2B? Go for it. Okay, I got this. Okay, how about draw an ionic compound with a formula AB? Be careful. See if you're paying attention. Go for it. All right, this is what I came up with. Now, you didn't have to draw quite so many, but how many blue A's do I have? I have 6. How many red A's do I have? I have 6. So it's a 1-to-1 ratio. All right, but I just didn't draw one A and one B. Okay, so there's a very distinct difference. Now, if I were doing it maybe a little bit better, I'd put little pluses and minuses in here. I don't know what elements they are, so I don't know what charges they would carry, but it'd be the same. So this could be a +2 and a -2. I mean, or a +3 and a -3. I don't know, but for that reason, you would have a 1-to-1 ratio. Okay, so almost done. So classify each of the following as atomic element, molecular compound, or ionic compound. If it's an atomic element, classify as monatomic or polyatomic element. Go for it. So pause this and see how you do. All right, welcome back. This is what I got. Hopefully that's what you got too. Okay, hopefully there's no problem. Xenon is not a Hofbrinkel or phosphorus or sulfur. Bromine is a Hofbrinkel. Fluorine is a Hofbrinkel. I guess you could have said polyatomic or diatomic. This is an ionic compound, another ionic compound, molecular compound, and again, atomic element. So that's our last problem until we're done. So problem number 4, which statement best summarizes the difference between ionic and molecular compounds? Go for it. Pause this, read them, and circle. All right, welcome back. I picked B. I don't know about you. I think it describes it the best. All right, this one is really wordy, and I didn't talk about directional forces, and I'm not really sure what this all says. Some of it's true. All right, there is a formation of ionic lattices. All right, which is extended networks of alternating cations and anions. All right, but what's this about the highly directional bonds? I'd hold off on that, all right? I don't really know what that means yet, okay? But look at letter B. I think this works out. Molecular compounds contain covalent bonds in which the atoms are going to share the electrons with the other, resulting in this new force called a covalent bond that holds it together. All right. Ionic compounds contain ionic bonds, which one atom donates electron or electrons the other, resulting in this ionic force that holds those ions together, like a magnet would. So what's wrong with letter C? There's fewer words here. I mean, maybe it's good. All right. I don't know what covalently bonded molecules are. I needed a little bit more detail than that, like sharing electrons. Ionic compounds is composed of ionically bonded what the heck is that? All right. Also, I would not necessarily word ionically bonded molecules. That's not always a great molecule. Kind of implies covalent, so I don't like C very well. All right, so I think B is the best, and that is it. So guess what? I'm done. So don't wait to be great. See you next time. Bye bye.